Hello all and welcome to this first video in our series of videos where we look at discrete random variables and their probability distributions. As you can see, we're hopefully going to only take 2 weeks for this, and if that, even a full 2 weeks. So let's get straight into it. For practice, try and do as many problems as you can. The first couple exercises probably going to be able to meet your point of need fairly quickly, so you might be able to skip some of them. So for sections A and exercise A and B in particular, it might not be all, but certainly for exercise D, where we get more into the actual probability distribution stuff, then you'll certainly need more practice. Right, so the rest of this video, it's going to be pretty informal because most of this is just a review of a year 8, 9, 10, and 11 probability work. So we're going to try and get through exercise 13A and 13B material fairly quickly. Right, so exercise 13A, sample spaces and their probability. A quick reminder straight off the bat, for all probability stuff, if you're ever finding a probability and you get an answer that is either less than 0 or greater than 1, it is wrong. Probabilities are defined between 0 and 1. Okay. Your probability of whatever event can only be between and up to including 1. Okay, can't be greater than 1, can't be less than 0. So if you get an answer outside of that, you're wrong, you need to go back to check your work. So that's a great check. Right, so sample spaces. So a sample space is the set of all possible outcomes. You'll see this word set come up quite a lot, but sample space, all possible outcomes, and it's denoted by the Greek letter epsilon, that sort of weird looking E symbol. So yeah, that just lists everything. So for a 6-sided dice, the possible sample, the total sample space, possible outcomes, is 1, 2, 3, 4, 5, and 6. So in that case, that's our sample space for a dice. An event is some subset of it. Can be how you define it, could be how someone else defines it, doesn't matter, but it could be, it's an event related to that sample space. So here's the interesting thing, event starts with E, but the Greek letter epsilon is used for sample space, which is S. So this is where we've got to be careful with our notation and realize what's what when we're talking about. So for example, an event could be an even number when a 6-sided dice is rolled. So if we think of what are all the possibilities when we roll an even-sided dice, well, that is 2, 4, 6. So that is the possible outcomes, or that's what A, if we said A is defined, as we've said there, then A is equal to those outcomes. Possible outcomes. Key thing to note in this, there is a very distinct difference between writing A equals, A being the actual event, because that means we then need to write a list, okay, of all matching outcomes, versus probability of A equals. That will be a number between 0 to 1. Okay. So if we just have the letter itself that is the name of the event, then we have to be writing a list. If we've got probability of it, well, then we're actually calculating the probability. And we've got a Venn diagram over here to represent that situation. Right, a couple of things we've seen before that we can define is, say, if we have 2 events. So here we go. So A is an even number when a 6-sided dice is rolled. So we have the same, A is equal to 2, 4, 6, as we've got it written there. And then B is considered a number greater than 2 when a 6-sided dice is rolled. So B is 3, 4, 5, and 6. Now union, that's what this U symbol here is equivalent to either event A or event B, or both. So it's one, the other, or both. And as we can see here in this Venn diagram, we have the 2, 4, and 6 in A, we have the 4, 3, 5, 6 in B. Union is in A, in B, and in both. So we get for a union is 2, 3, 4, 5, 6. Now the way I remember this one, and I remember the union first and then the intersection from it, is a union is like a marriage. What is mine is yours, and what is yours is mine. Whatever we have, it belongs to both of us. So yeah, union is a marriage of the events, one, the other, or both. Well, intersection, okay, which is represented by this N-looking symbol, is what two things have in common. They have to be in common. So again, we have our situation of events A and B. The intersection. Okay, this is our intersection. Is what do they have in common? Okay, while union up there was one, the other, or both. Right. Solving problems or finding overlaps. There's a couple of different tools that you can use that you've seen before. You've seen Venn diagrams, probability tables, also called two-way tables, also called Carnot maps. I never remember how to pronounce it properly and how to spell it. Starts with a K. They are all roughly the same thing, slightly different in how it's entered, but they look very, very similar. So we have all these tools available. So when should we choose one over the other? If an outcome only has one event, it's suggested to use a Venn diagram or probability table. I would also say that you should, where possible, also use a probability table because that's going to give you greater information than a Venn diagram and allow you to interpret the data a little bit easier. So I would always suggest if you only have one event, then use a probability table. If an outcome has more than one event, so multi-stage. So for this example here, it might be drawing a heart or not. That's a single event, single stage. While if it has multi-events, so it might be first step is heart or not, and then after you do that, you might roll a dice. Okay, so we've got two steps or two stages going on. You want to use a tree diagram, and that will help you see possibilities and probabilities. If an outcome has lots and lots of events, then we'll use a distribution, which we'll cover later on in the course. But for now, I'm going to suggest probability table or tree diagrams are going to be your two tools that you want to go to. A couple rules on events and sample spaces. The probability of A being where, and this here for all events, or where we can just write the word where, A is, this symbol means subset. Okay, so A is some part of the sample space. So again, we think of the whole sample space is 1, 2, 3, 4, 5, 6. And if we're saying A is some subset of it, it means it has to be some part of it. Maybe it happens to be the 1, 4, 5. Then that probability of A, since it is part of the sample space, the probability is equal to or greater than 0. The probability, so that's sort of rule 1, probability of the whole sample space needs to be equal to 1, which makes sense. If you include the whole sample space, you have no alternatives. That means that event is certain. So the probability needs to be equal to 1. Rule 3 is another way of just saying that exact same thing, but in words, the sum of all probabilities of all outcomes of an experiment is 1. If you sum up the probabilities of all options, it must be 1. Probability of the empty set, this symbol here is represents the empty set, which means effectively nothing. So you could write it as the empty set is equal to nothing. And the probability of that's going to be 0 because it's nothing in it. It's not even saying 0, it's nothing. So the probability of that occurring is 0 when we have some form of event occurring. The complement of a probability, so A dash here, that A dash means complement, means the opposite. So let's say A is equal to getting a heart, that means A dash must be not getting a heart. Okay, so it's just the opposite. And the probability of the complement is equal to 1, take away the probability. So say if we say the probability of getting a heart is 1 over 4, that means the probability of A is a quarter, while the probability of A dash is equal to everything other than that. That's what not effectively means. That means everything else, take away the probability of A. So we get 1 take away quarter is equal to 3/4. That's that. And then the very last thing is the addition rule. And this comes up lots. Okay, this whole rule here. Okay, and I know I've said before using two-way tables is preferred, but to represent what this rule is actually talking about, it's easiest shown with a Venn diagram. Okay, so the probability of A union B, which means all of this, and we'll say that side there is A, that side there is B, the probability of all of that must be equal to, okay, let's put that is equal to the probability of A. So let's put all that in blue. And I'm going to highlight that in green, get some colors going on here, plus the probability of B, which is in red, all this here. Take away the probability of A intersect B, which is the overlap in the middle. Now, why do we have to take away that overlap in the middle? If we look, we're counting it once when we're doing the probability of A. Then we're actually counting it again when we do probability of B. We're getting it twice, so that's why we have to take it away. So the addition rule is, let's undo that. It's not letting me. Okay, that's what the addition rule is talking about, and that allows you to link probability unions and intersections. It gives us sort of a connection between these two and how to, and you can just rearrange this like any sort of expression or equation using inverse operations. Right. If A and B, and this is a big if, A and B have nothing in common, okay, that is the intersection is the empty set, it has nothing in it, then the addition rule can be written as the union is equal to just the probability of A plus the probability of B. But that has that big if, okay? So that needs to hold true to use this simplified rule. Right, so using that, let's do a couple quick problems. If one card is chosen at random from a well-shuffled deck of 52 cards, what is the probability the card is a queen? Well, there's 4 queens in a deck, so we'll call that event Q, and that's going to be equal to 4 on 52, which is equal to 1 on 13. Not an ace. Well, as soon as we see a not, this is when it should be ringing alarm bells to maybe try and use the complement. Instead of figuring out, well, how many cards are there that are not an ace, especially when you get something like here where it's not either an ace or a 9, then using complements is a lot easier. So I'm going to say getting an ace. We're going to call that A, and we know the probability of getting an ace is same thing, 4 over 52 or 1 on 13. So the probability of not getting an ace is the complement of that, which is equal to 1 take away 1 on 13 is equal to 12 on 13. You could have also known, if you know a deck of cards really well, you would know that there's 46 cards that aren't an ace in it. 48. And you could do 48 divided by 52, which does simplify into 12 over 13. Right, getting a jack or a spade. Okay, so if we want to write this out in full, that is equal to probability of a jack or, and in probability and or, we can consider that sort of a union because it's a jack or a spade. Technically, we could accept a jack that is a spade. So we're getting a jack union spade. which using the, we can use this addition rule now. We're trying to find the union, is equal to the probability of a jack plus the probability of a spade, take away the probability of both of them, intersect spade. There we go. So the probability of a jack, how many jacks are there in a deck? That is 4 on 52, which is again 1 on 13. Plus probability of a spade, there are 13 spades in a deck, which is 13 on 52, which we can write as quarter, because a quarter of the deck is spades, minus how many jacks are spade? Well, that's only 1 on 52. And just to save time, you could then get common denominators on all those fractions and solve, but I'll leave you to do that. And lastly, either an ace or a 9. Very similar thing, that is the probability. No, this is a little bit different, because an ace or a 9. Oh, no, we can use the same thing. The probability of an ace or 9, so or is a union, or a 9 is equal to the probability of an ace plus the probability of a 9, take away the intersection of them, ace intersect 9, and this is where we're coming back to this simplified rule. Is there a card that is a 9 and an ace at once? And we would realize that this here, ace intersect 9 is an empty set. There's nothing in it, so we can actually just make that go away. So this is equal to probability of an ace is 1 on 13 plus probability of a 9 is 1 on 13, which is equal to 2 on 13. So there's some examples of using the addition rule, either with an included intersection or when the intersection is an empty set. They have nothing in common. Right, some frequency tables. Another way that we can determine probabilities is by actually conducting experiments, doing many repeated trials, and collating our results in what we call a frequency table. So here is a frequency table for an experiment being carried out twice, rolling a 6-sided dice 1,000 times. This is rolling it 1,000 times here, and then repeating the experiment here. You can see even doing 1,000 trials, we still get a bit of variation. We can see that it comes up. We know that the expected probability should be 1 on 6 for any number, but when we do the actual experiment, we get slight variations. And this statistical variation is what we'll look at a lot in Chapter 17. But let's get into using one of these. Estimate the probability of observing a 3 when this particular dice is rolled. So we can see here that rolling a 3 occurred 165 times. So the probability of a 3 experimentally, according to this, is equal to 165 on 1,000. And I'll leave that to you to simplify. From this, which outcome would you expect to be the most and least likely on the next roll of the dice? So we just need to look at our table and identify what occurred the most and what occurred the least. And we can see that a 2 occurred the least at 160 and a 4 occurred the most at 175. So the most likely is a 4 and the least likely we expect is a 2, according to our experimental data. Rightio, lastly, suppose that practice using some probability tables. Suppose that 65% of the students at a certain university are studying commerce, and that 30% of the students, so this is students in general, are in the first year, and that 15% of the students are in first year and are studying commerce. Okay, so how do we break this down? So we need a two-way table, or a Carnot map, as they're also called, which we set up like follows. There we go. Okay, and we're going to put one event, or call event 1 over there, and we're going to put event 2 here. So event 1 is commerce, studying commerce, or the complement of it, not. Same for event 2, the student is in first year or the complement of it, which means they are not. Now we can just start filling in details. So, studying commerce, so 65% of students are studying commerce. So that means 65% of all students, so that means we have to put 65% down here. 38% of students are in the first year. That means so 38% of all students are in first year, so we can put that here. And then finally, what colour can I use? Green. 15% of students are in the first year and studying commerce. So they are in the first year, are studying commerce. That makes 15%. Okay. So this is where we need to be really careful with this. Okay. Currently, I've entered these numbers as a probability of the whole student base. Okay, so it's 15% of all students, not 15% of the 65% that are studying commerce. Same here, it is 15% of all students studying first year. It's not 15% of this 38% over here. So using percentages is okay. Sometimes you're given explicit numbers and it might be a ratio of 30 out of the 60 studying commerce are first years. Well, if you have 60 here, you just have to be really careful how you're assigning numbers. Now, the thing that we know is that all students together must then equal 100% of the population. So we get to put this in here, and then it's just a matter of filling in the blanks. There we go. We're up to 22 minutes already. Wow. Right. So if 38% of all the students are first years and 15% of them studying commerce, that means over here we have to have another 23% that aren't studying commerce to make up the 38, and then we can just keep applying this sort of deductive reasoning to fill in the rest. 65, that must mean that's 35%. Working down this way, 23, 35, that must mean that's 12%, and that must mean that is 62% going across that way, 50 plus 12, and then also checking down here, 38 plus 62 does equal 100 as well. Right, and my cat's going to come and try and join me, so I apologise for the noise. 1 second. Rightio. We'll do this one last slide and then we'll end the video here. So when are we going to get through exercise 13A? Right, suppose that, so this is our data that we were just given, okay? What is the probability that a student not in their first year will be studying commerce? So we need not first year and studying commerce. So the way I do these is go back to the two-way table and I just circle in grey lead, I would suggest, and when you're doing it on paper, is circle these conditions and then look where they line up. So not first year means here, and studying commerce means here. Where do they cross there? That's 50%. So it's actually 50% is the probability. What is the probability that a student is not in their first year and does not... Oh, no, I've made a mistake in this first one. And this is what I was getting at in the previous thing. Okay. Right. Here we go. What is the probability that a student in the first year? So this is actually giving us a condition. And we'll get into this a little bit more in the next exercise. What is the probability that a student not in their first year? So we're now actually, in this problem, we've restricted our population because we're told that they're not in their first year. So we're restricted to this. Okay. So that a student that's not in their first year will be studying commerce. So we've restricted the population and we're down to this. So we can see that, yeah, it's 50% of the whole student body, but it's 50 out of 62 if we consider just not first years. So this becomes probability is equal to 50 out of the 62, and then you can stick that in your calculator and we'll get 50 divided by 62, 25 on 31. Okay, or that was 0.80, which is roughly equal to 81%, which makes sense. 50% of all students out of this 62. Yeah. Cool. So yeah, we have to be really careful when we're reading this, how to interpret, because there was no and. Yeah, there was no word and, so that wasn't a union or an intersection. Okay, what is the probability that a student is not in their first year and does not study commerce? Okay, so this is where it's that union sort of situation. Not in their first year and does not study commerce. So we aren't restricted anymore. It's just a combo situation out of the whole student body. So what was it? Not first year, does not study commerce. So not first year, not commerce. That's 12%. So 12% of the whole student body is equal to 12. There we go. And we could write this as probability F dash intersect C dash. Cool. Yeah. And we'll come back to, in our next video, what the notation is for that. Right, 26 minutes. Geez, didn't mean for it to be that long, but we've got a bunch of worked examples there. If you have any questions, let me know, put in the comments below, or ask in class as normal. Thanks and have a good evening.